right, let's go ahead and get started here. Several folks are still joining, but we're tight on time and like to be on time. Good morning and thanks for your time and participation in today's webinar. My name is Scott Johnson and I'm the Global Business Manager for Advancion Paints and Coatings. Today, we're really excited to share with you some new information about a new product, including our latest application research work that highlights the unique performance and functionality of DeMopa, which is our new-to-world multifunctional formulating ingredient for high-performance industrial coatings and ink formulations. Our goal today is to also provide you with a venue to ask technical questions of our dedicated coatings application team who are on the line today, so that you gain a better understanding of the performance benefits and value that can be achieved using DeMopa in your formulations. To ask questions, please use the chat or Q&A functionality available in the WebEx application on the right side of your screen. We will collect your questions throughout the webinar and we will address them at the very end of the presentation. So in closing, again, I appreciate your ongoing interest and engagement with Advancion. We're really excited here to talk about something new to world, which doesn't happen all the time. So appreciate your time today, and I will turn the webinar over to our host today and our customer application specialist for Europe, Middle East, and Africa, Dr. Sadan Rezagia. Sadan?
Good morning for all of you. Thank you for joining us for this webinar. Today I'm going to talk about a new product, new additive called DeMopa, which is dedicated to industrial coatings and water-based industrial coatings and ink applications. Next slide, please. You know, Advancion, we are a manufacturer of multifunctionality additives and intermediates, as well as some nitroalkane solvents for diverse applications and markets. We have two production sites, one in US and one in Germany, and we have an extensive record in innovation and technical solution development. We have 6 R&D application centers located around the world, and we are responsible care, and we have a department dedicated to any question concerning regulatory here in Europe and elsewhere in the world. Next slide, please. We are here presenting our new additives, N,N-dimethylmethoxypropylamine, which we call literally DeMopa. You know, probably most of our amino alcohols, ANP is the oldest version, introduced very long time ago. The basics of our chemistry comes from these molecules, and most of them, they are combining a primary amine or tertiary amine and some hydroxy groups. If you take a look to the left part of the slide, you see that we have 3 amino alcohols combined, having, you know, primary amines, which are most of them, especially AMP, 2-amino-2-methylpropanol, and the second one, AEPD-VOX-1000. Both have been incorporated and valued in a lot of architectural coatings. In the left part, we have the tertiary amine containing amino alcohols, the DMANP80, which is the 2-dimethylamino-2-methylpropanol. And the new one is, of course, the DeMopa. The DeMopa has the particularities that it doesn't contain any hydroxy group. So we will see on the next slide that it has some versatile applications. Next slide, please. Can you make it bigger, please? No. So DeMopa is used in a because of, thanks to its balanced properties, it can deliver some advantages in performance in water-based systems, and can help, you know, to transition to water-based systems and replace solvent-based systems. If you take a look to the right-hand side, you see that the MOPA is the MOPA. Sorry, yeah. If you take a look to the right-hand side, you see that the MOPA has some polar group. The polar group coming from methoxy group gives some solvency properties. It's like it acts like coalescent. At the same time, it is quite good solvent for the wide range of binders. It has a very high absorption at pigment surfaces, titanium dioxide, organic pigments, and recently we have also some work on anti-corrosive pigments. It is inert. The fact that it doesn't have any hydroxy group and a tertiary amine brings us to propose it as a catalyst for 2K system, reactive systems. It is a good buffer, and it has the possibility also to neutralize because it's a base. Keeping always in the right-hand side, it's an inert particle which has no reaction in reactive systems. Being catalyst with no reaction, this means that it will not create any, let's say, side reactions, high compatibility, and also a lower viscosity. In terms of odor, the odor is mild. If you move to the left-hand side of the slide here, we have a versatile solubility of the MOPA. The MOPA is soluble in water. The MOPA is soluble in polar solvent, being polar, so it is soluble in polar solvent, and it is also solvent in mineral oil in general. The MOPA is anhydrous. This means that it doesn't contain, or it contains a low portion, very low portion of water. So it is compatible with reactive systems. The MOPA also has a very nice volatility in terms of being, early eliminated during the drying process. The MOPA has a fast evaporation compared to conventional ethanolamines, and it has the capability to form an azeotrope with water. Azeotrope with water, this means that during the grinding step, it could drain, let's say, the traces of water coming from the dispersant or coming from the different components of a reactive systems like polyols, and can, let's say, drain water, help the drying time, reaching a better chemical resistance and water resistance as well. And in one system that we have tested, we demonstrated that the MOPA can reduce the cure temperature of polyol melamine systems, 2K systems. So if we move to the next slide, we will see, next slide, please. We will see the properties of the MOPA compared to competition. Most of the competition here is DMEA. The MOPA has almost the same pKa as DMEA. The MOPA, due to its high volatility and possibility to form an azeotrope of water, we will see this in the performance of coatings in general. It has, as I said, a better wetting, an excellent wetting for pigments, all of pigments, titanium dioxide, anti-corrosive pigments, and organic pigments. It is a good compatibilizer if we have, let's say, acrylic systems or PU systems or blends. Traces of the MOPA can help to compatibilize blends. Inert catalyst, in the sense that it is an inert tertiary amine. Anhydrous, as I said, and the polarity is the same as when we have a hydroxy group. This means that we could not expect any reactivity with the MOPA in 2K systems. Next slide will show. In this next slide, we are going to cover the different applications of the MOPA in water-based system and reactive system. I put here the possibilities of, let's say, bringing DeMopa in use in water-based systems and reactive systems. First of all, we have the properties of DeMopa that we can use, and then we link these properties and functionalities to the application. In which kind of water-based application this will be helping in bringing performance. The next slide. We will cover here. The use in water-based formulation systems. This means we will cover here, we take the table, the slide, the last slide, and we will concentrate on the formulation side, only on the formulation side, where DeMopa has a higher capability has a high capability in pigment dispersions of titanium dioxide, organic pigments, and anti-corrosive pigments. Due to the fact that DeMopa, as I said, has a high volatility during, let's say, the drying process, we will see that DeMopa will keep a low residual amine in the coating, and this will contribute to reduce the water resistance and the chemical resistance. DeMopa will produce also a low foam, and because of this high capability of dispersing, wetting the different pigments listed here, we can have access to produce a higher solid content in the slurries, or even increase the solid content of the formulations, keeping the same, let's say, level of viscosities that is adapted to the application side. And these properties, we can link them to direct to metal applications, where we can find different systems. It can be acrylic, basic acrylic, or a blend of acrylic and PUD. It can be also in wood coating, where DeMopa will disperse the pigment or part of the pigment, and even in translucent and transparent coatings, it will deliver something which has low residual amine content, less hazardous on the wood, and also transparency, which is quite good. And in case of reactive systems, the fact that amine will leave very early, it will produce something which has a better hardening because of the cross-linking. And then, based on that, this is typically on the formulation side. If we move to the next slide, we will see that some people, we will see here that in the styrene acrylic or pure acrylic industrial applications, which we commonly call direct to metal, where we need to protect the metal, the contribution of DeMopa or any amino alcohols, DeMopa is performing better. You will see in the next slides. But basically, what we are doing here, we want to go in this direction, where customers are looking for reduction of VOC, improvement of the environmental impact, and of course, targeting, the quality of the final coating on the metal, where corrosion resistance is very important, adhesion on the metal, and also the early water resistance, as well as the scrub resistance. Next slide will show how DeMopa. Yeah, we are here. Next slide will show. Yeah, this one. Next slide will show the typical formulation that most of the customers are using in here. We are comparing DeMopa to DMEA, to ammonia, and we are introducing DMANP 80. And what we recommend, most of our formulations, we recommend, as DeMopa is a good wetting and dispersing agent, to use DeMopa and any amino alcohols in the grind. And this is what we do it in the lab. In the formulation, you see that there is no anti-corrosive pigments. We demonstrate only by, let's say, a version coating without any anti-corrosive pigments. The only product that is used here to, let's say, limit the corrosion is the flash rust. I mean, the beginning of the corrosion using the flash rust. In this kind of formulations, we have demonstrated, in the next slide, please, you will show that from this test, which is very important for to demonstrate the capability of DeMopa, this is what we call the dispersing demand. Dispersing demand consists of having a large amount of titanium dioxide, put it in water, and then disperse it. When we disperse it, we add a dispersing agent here. We took Tamol 851, and we, of course, when you do it only with only the dispersing agent without any neutralizer, you will see that you need to have a lot of amount of dispersing agent to enable, in order to reduce the viscosity of your system. So this viscosity drop will take place only when you have high concentration of dispersing agent. Without a neutralizer, you see the curve, the black curve. And if you choose to work with ammonia, a low concentration of ammonia, you see in the green curve that you are improving a little bit the dispersibility of the titanium dioxide, but it keeps not far from the case where you are only using a primary dispersant, Tamol 851. If you add DeMopa, this low concentration at 0.05% based on the pigment slurry, you see that the drop of the viscosity takes place very early at a lower viscosity level, and it will also take place with less amount of the dispersing primary dispersant. This means that DeMopa will help to reduce this primary dispersant, which is most of them, are highly hydrophilic, and DeMopa will make your slurry less hydrophilic and more hydrophobic, and this will help in improving the water resistance, and especially the early water resistance. So you see in here that the dispersion of titanium dioxide is significantly improved by DeMopa, and DeMopa can also give an opportunity to optimize the formulation and use less dispersing agent, which will allow for a better cost optimization, or even better, let's say, hydrophobic resistance, hydrophobic behavior of the film. Next slide will illustrate this hydrophobicity when we are using DeMopa. In this case, what we are showing in the left-hand side, how early water resistance is going to be improved. We make the paint in same thickness applied for all the three systems using ammonia, DMANP, and DeMopa as an additive, as a wetting and co-dispersing agent. And we see in the early water resistance, when we are considering the system at 2 hours and 4 hours, we see that there is a big difference in terms of improvement of this early water resistance, especially after 4 hours. We see with ammonia, the color changes moderately. With DMANP, it changes also moderately, but with DeMopa, due to the fact that DeMopa is leaving very early, we have a very, very slight change in color. And if you take a look to the blistering, we rate here the blistering. Our blistering rate is better compared, when we are considering the use of DeMopa instead of both DMANP and ammonia. We did the same on the paint formulation, where we want to show the improvement of hydrophobicity related to the scrub resistance. DeMopa, due to the fact that we can optimize on the use of the primary dispersant, can achieve, especially on the paint, can help achieve a higher scrub resistance compared to ammonia, and even for some cases where DMANP is not used correctly, DeMopa is definitely the best candidate when we are considering interior paints for scrub resistance. Next slide. In this next slide, we are moving to another kind of formulations, direct to metal, where we include let's say anti-corrosive pigments. We took representative anti-corrosive pigments from zinc phosphate to zinc modified phosphate, and we took also two calcium based, which are the next generation, especially the last one, which is without any phosphate. And we did the work using DeMopa comparison to ammonia in the grind, of course. We were covering the percent of anti-corrosive pigment between 4 and 8. Titanium dioxide kept at the same level, and we of course at the end we can neutralize with ammonia, or we can also neutralize with DMANP. In terms of use of the weight of amino alcohols compared to DeMopa, we are operating at the same level. And the next slide will show, the next slide will show here the particle size, how the particle size of these anti-corrosive pigments are deflocculated, are disaggregated, thanks to the use of amino alcohols. We do the test in slurries, in water, and then we measure how particle size is decreased. So if we take the ammonia, which is typically used in anti-corrosive pigments for exterior, you see that the deflocculation or disaggregation of these pigments keep at a higher particle size. It's completely inefficient. We get something like 5, let's say between a medium range of 5.5 microns, which is quite hard. And this kind of, anti-corrosive pigments at this level, they are not at the primary particle. They are not at the lower, let's say, lower particle size, which is able to give a benefit in terms of anti-corrosion pigments. But as soon as you use in the same proportion, in the same, let's say, molar proportion compared to ammonia, as soon as you use one of our amino alcohols, AMP, DMANP, DeMopa, and AEPD, you see that the particle size of these anti-corrosive pigments decrease significantly to a range of, let's say, medium range of below 1 micron, which is very good. And DeMopa is the best performing. If you see here the minimum and the maximum distribution of particle size using DeMopa, DeMopa is the best. This means that the absorption of amino alcohols, DeMopa, on this kind of anti-corrosive pigments will bring a huge improvement in anti-corrosive paints. The next slide will show how in a paint system Here we are considering the paint system initial and after 1 month aging. And we are following how the pH stability will evolve between this period. And you see that the delta pH using ammonia is quite large. And we know this from the marketplace, that people sometimes are arguing that from batch to batch they have a variety, different values of pH, and they know that amino alcohols will bring this pH, to a smaller, let's say, a better control of the pH, and this delta pH, especially with the DeMopa, is doing very well. So ammonia provides very poor stability, whereas all the amino alcohols are doing very better, drastically better. If we move to the next slide, which will, we have here plotted the dry opacity, the contrast ratio between the different systems. We see that with ammonia, the contrast is at a lower level compared to all the amino alcohols. And we see that DMANP is improving better. So DMANP and ANP are the most efficient multifunctional additives for dry opacity. And DeMopa is not bad at all because it's performing better than ammonia. The next slide. The next slide will show the anti-corrosive properties of this formulation that we have shown before. In the left-hand side of the photos here, you see when we are formulating with ammonia, we have a problem in optimizing, in getting, the anti-corrosive pigments at lower level. We need to go to 8 parts of in the formulation of this zinc phosphate in order to perform correctly in terms of anti-corrosive properties. But as soon as you consider using one of these our amino alcohols, ANP, DMANP, DeMopa, you can reach this performance of anti-corrosive properties with half amount of this anti-corrosive pigment zinc phosphate. And you see in here that on the strike, DeMopa is performing slightly better. We don't have any blistering. We don't have any staining on all of the amino alcohols, and DeMopa is doing better. So from here, we can understand that there is a high possibility, high opportunity here to lower the proportion of the anti-corrosive pigments by 50% or even more. This will play on the cost of the anti-corrosive properties. Just to mention here that all of the work that we have we are sharing today, we did not consider playing on the dispersing agent. From past work, when we introduced ANP and DMANP, we have been showing that ANP and DMANP can help us reduce the proportion of the primary dispersant. And in this work, if some customers choose to work on DeMopa, you have the possibility also to play on the formulation and reduce the primary dispersant. And we recommend to do that because you will add even a higher hydrophobicity to the final paint, and probably you will increase, for sure, you will increase the barrier properties and the anti-corrosive properties. Next slide. Yeah, the next slide will show the benefits in direct-to-metal coatings with anti-corrosive pigments. Amino alcohols are efficient. With all of the anti-corrosive pigments here, we have high base strength amino alcohols like using, ANP, DMANP, and DEMOPA. DEMOPA is doing really very good improvement, like DMANP and ANP, and we cover all of these improvements in pH, color retention as well, opacity, gloss, wet adhesion, and corrosion resistance. And finally, I add to that, we said it already, that we have the possibility to reduce the anti-corrosive pigments by up to 50% weight on the final formulation, and possibility also to play on the dispersant surfactant and make the system even more hydrophobic. Next slide. Next slide. Here we move to ink formulations, water-based ink formulation, where we have, for those who are who know the Flexo ink formulation, we have 3 steps. In the first step, we are producing the resin solution, where we are neutralizing the acid binder with amino alcohols. And then we take this resin solution, we use it in a pigment paste, where we are doing the grinding here. We took the carbon black as a reference here to carry the work. The mix of the resin solution, which contains amine here, will help also in the dispersion of carbon black. And then at the end, what we are doing here, we take the pigment paste and then we neutralize with some additives, and we end up with the final ink. So there is 2 opportunities here to use DEMOPA or any amino alcohols. The first one is in the preparation of the resin solution, and the second one is small amounts to neutralize the system at the end and to get it at the right pH. The next slide will show how DEMOPA can improve in ink formulations. We are taking here the resin solution composition, where we have the acid acrylic, styrene acrylic resin. We are neutralizing here with DEMOPA and compare with the same control using DMANP. And what we have seen is that the dissolution time, the solubilization time using DEMOPA is 1/3 of the time needed to dissolve with DMEA, which is a good thing that can help, reduce the batch cycle time of resin solutions. This is quite showing, that a better solvency properties of DEMOPA can improve this solubility time reduction. The next slide will show how DEMOPA, the volatility of DEMOPA, can help in the drying process. In the ink, the drying process is very important. So we are comparing here again DMEA based resin solution and DEMOPA based resin solution, and we are applying, heat, gradual heat from 120 up to 140. The starting solid content of the resin solution is 43%. We calculate it from the last slide. So in DMEA, when we are exposing our product to 120 degrees C, then 130, and finally at 140, we see here that the solid content is decreasing. Of course, we are eliminating the DMEA, but we are not eliminating DMEA as in the case with DEMOPA. With DEMOPA, very early at 120 degrees C, the solid content moves. We are eliminating a lot of DEMOPA, and if we increase the temperature up to 140, we get the system completely out of any amine residual in the coating. And that's very good because it will give the ink the properties of being less moisture resistant and less water resistant. And we will see this in the next slide, where we take the resin solution and we let it we take the resin solution, which is completely dry, and then we dissolve it in water. We dissolve it in water. We wait until 2 days where we have water immersion, sorry, and we see in the left-hand side the traces of DMEA keeping in the dry resin will dissolve and make some opacity in the water. This means that it can dissolve the resin. The traces of DMEA dissolve the resin, whereas with DeMopa, there is no traces of amine and the water keeps very clear. And this is due to the high evaporation of DeMopa. If we take the final ink formulation, which, as I said before, a combination of the resin solution and the pigment paste, after neutralizing, of course, if we do that and we compare how, if there is any color strength improvement in here, what we have seen here is that the color strength is equal, they are similar, but in the next slide, again here the sensitivity of water, next slide, not this one, yeah, this one, the traces of DMEA, residual DMEA in the system, when we are doing an immersion test, we have here the same film thickness, of course, applied on a card, dried in the same conditions. And when we are doing the water immersion test, we see that there is a solubilization or some whitening with DMEA, which do not occur with the DeMopa-based final ink. This volatility can bring a high improvement in flexo inks. The next slide is to show how, I mean, we need a lot of work covering the different pigments that we have listed so far. Carbon blacks, of course, titanium, where absorption is very good. And we are here considering organic pigments. Organic pigments in a test which consists only of measuring the adsorption on the pigment. We take the pigment in the water. We put a controlled amount of amino alcohol. It is here, you know, either ANP95, DMANP80, or DeMopa, and we shear for a certain time. After that, we are doing a centrifugation, and we take the upper part or liquid part of the after centrifugation, and we titrate. And we can measure how much ANP is in the water phase, the liquid phase, and by balance, we can calculate how much is kept in the dry solid of the pigment, which stays on the bottom of the after centrifugation. Based on that, you see that the adsorption of pigments is in the y-axis, and in the x-axis we are showing the types of the pigments we have been covering, from the red here to the we have covered 5 organic pigments. We have included also 2 carbon blacks. One is specialty, mostly used in automobile applications, where we are looking for very high quality of paints. And the other one is general purpose carbon black. And you see that the adsorption for the organic pigments, the adsorption vary from, due to the hydrophobicity of organic pigments, it's varying. AMP is not, I mean, ANP is performing quite good, but not in all of them. For example, for the red one, ANP is not the right solution. But for the others, especially the PG7, the green one, and also, let's say, I see it very small, the PV23, which is the violet, we have good performance. But if you take a look to what is the performance of DeMopa, since this is the object of this presentation. DEMOPA in the blue bars here are showing very high improvement compared to DMANP and ANP with organic pigments and to carbon blacks. So this is a good proof that DEMOPA is a good candidate to consider to make organic pigments and also to cover inks, including blacks or even organic pigments for inks. That's why we can claim that excellent absorption on DEMOPA can bring value for these water-based inks and inks in general, and this high absorption is due to the high wetting dispersion of DEMOPA. Next slide. I will conclude here on the benefits of DEMOPA in water-based inks. Fast resin solution, low foaming, retention. The surface tension DEMOPA is somehow showing a surface active capability. The fast evaporation will help of DEMOPA compared to DMEA will help to have less retention of DEMOPA, less residual amine compared to DMEA, and this will help to accede to a better water resistance of the finished inks. And finally, the excellent absorption of DEMOPA on carbon blacks and organic pigments is proved in here. The next part of the presentation will cover how DEMOPA can be used in the binder preparation. In the binder preparation, DEMOPA, we claim here that it is a stabilizer. It will stabilize being a base, so it will stick to any, let's say, carboxy group or any affinity in the pigment. It will stabilize in overall the slurry or the paint, and this will help in getting a better stability, better pH, better buffering, and at the same time, because of its high volatility, it will deliver early water resistance in the application markets, like people producing some PUD, where DEMOPA can be a counter ion of the carboxy group in the PUD. DEMOPA can also be a counter ion in the water reducible alkyds, and it can be also a good counter ion in the production in emulsion polymerization, where people are making styrene or pure acrylic dispersion. And in this topic, we move forward with the next slide, where in this kind of systems, the chemistry is quite clear. In the markets here of PUDs is quite versatile. PUDs are largely used in construction, automotive, furniture, textile, leather, and people are looking for systems containing only water, systems solvent-free in different applications, and PUDs or blends or mixtures of PUD with some acrylics are the solution to provide a better environmental profile and better VOC content. Of course, PUDs are less aggressive when they do not contain solvent. They are less aggressive on thermoplastic substrates or sensitive substrates, which do not like to have too much solvents on them. Regulatory, again, here is very good concern. DEMOPA will probably be better compared to traditional solvents like NNP and equivalents. And the next slide. The next slide is showing only the physics, the chemistry of that. DEMOPA will be a counter ion in the carboxy group for PUD synthesis. Whatever the PUD can be flexible or a little bit rigid by the selection of the polyol. And in the same time, in the alkyds, DeMopa also can be a counter-ion. Just to say here that we have a good positive from our customers using DeMopa in wood. Next slide, please. Using DeMopa in wood. In wood, we don't have too much data to share here because it's quite confidential. And what we know here is that people looking for a transparency or less hazardous or less amine residual on wood parquets, they are quite satisfied to have DeMopa due to the fact that water and chemical resistance are improved. Of course, DeMopa will leave. It will keep these two molecules from isocyanate and polyol to react and cross-link better. That's why the chemical resistance is better. And the hazardous improvement in hazardous, I mean, reduction in hazardous is due to the fact that there is no hydrophilic, let's say, products, residual amines in the system. Next slide. I do it. Next slide, please. In the last slide, we are talking here, we are showing here some data on the next slide, please, again. Next slide, please, again. Yeah, here in the DTM, from the past, we were doing direct-to-metal formulation based on acrylics for, let's say, simple DTM with monolayer or two layers depending on the thickness. And then here what we want to consider is the PUD, high-performing PUD, which can be put on top of one layer or two layers, and which are providing better corrosion properties with all the system, with the multi-layer system. The next slide will show what we have done in this. Next slide, please. What we have done is to formulate with white PU 2K water-based. The first part is using the grind, where we put an anti-corrosive pigment with titanium dioxide, and we put the amino alcohol in the grind. And then we have the let down, in which we have the polyol, and the different coalescent when we need a rheology modifier. And then it's a 2K system. We need some, at this stage, we need to have isocyanate to cross-link the system. The next slide will show how these 2K water-based systems are improved by using DeMopa compared to DMEA. The pot life of systems containing DeMopa are higher compared to DMEA. Why are they higher? Because DeMopa will leave early. Because DeMopa will leave early and the viscosity will build up faster than the system containing DMEA. The amine with DMEA will keep residual here and let's say avoid to have these reacting groups reaching each other. And the same way we measure the dry time using DeMopa and DMEA, we found out also, we prove again that DeMopa has a lower curing time. The curing time is given at 110, whereas with DMEA it's only 165. Next slide, please. Next slide, please. Hello. You hear me?
Yeah.
Next slide, please. I don't hear you. Yeah, next slide. In this next slide, we are comparing the dry film properties of paints containing DeMopa and DMEA, and all of them, they pass the different tests of pencil, adhesion, water, or solvent resistance, except that DMEA is bad in terms of salt spray. DeMopa is bringing better improvement in salt spray, we are here showing the test conditions where the test is showing that DeMopa is better. The next slide will show also the UV resistance color change where DeMopa is performing better, definitely better, especially after aging. The aging is done during 2 months. The whiteness is better. The delta E is better. The lower delta E, the better the system is. With DeMopa, the value is lower. And the next slide will show. And the next slide will show. Sorry, next slide, Scott, please. Yeah, the next slide in here. In here, we'll show the gloss measurements. We did the gloss at 60. Again, here, the gloss, the higher the gloss, the better it is, of course. And DeMopa, after aging, proves that it's better compared to DMEA. The same with the distinctness of image after aging, 2 months aging, DeMopa is performing better. Next slide, please. With carbon black, we have the same improvement. DeMopa is performing better initially, slightly initially in the beginning, but the improvement, especially with the gloss, comes is better with DeMopa, and the distinctness of image initial and after aging is better compared to DMEA. Next slide, please. Yeah, the summary in here is that DeMopa giving a reduction in a dry time, cross-linking is improved. DeMopa will provide a better film hardness compared to DMEA, and DeMopa will give a better weatherability in terms of gloss, distinctness of image, and color change. And the last part of the presentation will treat about the catalysis system. We go straight forward to the fact that we have DeMopa, which contains, as we said in the beginning, a tertiary amine, which could be an inert catalyst compared to DMEA, which also is a catalyst, but a reactive catalyst. And the next slide will show, next, yeah, this one. Now with the plot, please. With the plot, please. Yeah, this one. In here, what we demonstrated that DeMopa compared to commercial tertiary amine catalyst is doing very good in the sense that people are making prepolymers or cross-linking using catalyst. And the situation today is that people are trying to replace DBTL and they are going for new alternatives, and DeMopa can be a good alternative, like DABCOs are doing with this kind of 2K PU systems. And we see in the left-hand side the viscosity, the curing time. We are measuring curing time versus the molar content of the catalyst in the mix of TDI and polyol. And we see in here clearly that DeMopa is performing quite equally, especially at around 3-4 parts molar, equally to DABCO BL11, which gives an indication that DeMopa can be a competitive catalyst in a mix in PU 2K systems. And then the last slide will summarize in that in 2K TDI polyester polyol, it can be any polyol. We can also generalize this in aliphatic TDIs, and DeMopa can be a serious candidate to make, to be a co-catalyst or to be a sole catalyst in systems like this. And then I finish my presentation on the last slide, where I thank you. Yeah, we have been covering, these different applications, first in paint and ink formulation. Then we moved to the binder entities, and we finished with the cross-link capabilities. I thank you so much for your attention. And please, if you have questions, please go ahead.
Excellent. Thank you, Sidan. We did have one question. We will be sending out to this group and all registrants a recording of the webinar with our contact information and links to order samples. So we'll send that out shortly after the presentation.
Yes. Yes, I do it. Yeah.
Yes, I do it. Great. I don't see any questions this time. Okay, one question. In your opinion, can DMOPA bind to the protein fibers of leather? One area we have not studied. Sidan, any thoughts?
Yeah, I hear you. In proteins, whatever the system it is, if we want to absorb in any product, any protein or some other things, we need some acidity because the is a basic. So it needs to link with any acidity. If we take our experience with pigments, we know that titanium is a little bit acidic. Whatever the treatment, titanium, they bring an acidic group on it, which makes the absorption work good. For the anti-corrosive pigments, it's quite difficult. The same it is for the hydrophobic pigments like organic pigments. And especially carbon black, they are also hydrophobic by some functionality. We need to consider how proteins are functionalized, and I don't have any experience in that.
We can provide some follow-up on that also after the event. At this time, I don't see any other questions. So again, I appreciate everybody that's working our global applications teamwork, evaluating DMOPA and all of these new applications. And again, as a company, Advancion, formerly Angus Chemical, we're very excited to introduce a new to world molecule. Something, as you all know, is increasingly difficult in our regulated environment. We have commercial quantities available for purchase and for evaluation. So please feel free to reach out to us using the contact information we will send after the meeting. And we're happy to help you with your variety of applications in which you can look at DMOPA. So thank you for joining today. And with that, we will conclude the webinar.
Thank you very much.
Thank you very much.